Lately, I've been getting quite interested in alternator operation, guys, in the study of alternators, and I'm just kind of kicking around the idea, trying to develop a video and explanatory video on the concept of alternators. So I don't have an alternator to show you here, except for the one in my car. Unfortunately, you cannot really get inside the alternator with respect to tapping off each stator individually and seeing what's actually going on. But what I have here is a little DC brushless motor, and I'm actually using it as a generator, an alternator. So what I have here is just a tool, obviously, to drive this little DC brushless motor, but because we're driving it, we're using it in a generator capacity, yeah? It's there's 3 coils inside, so we'll call that 3 phases. We'll just call it the red, the yellow, and the green phase, because that's going to correlate to what I'm going to have on the scope. And we'll actually see if we can get an understanding for how this works. So this drive here, although it looks like it's going inside to drive the rotor, this motor is actually an outrunner, meaning this entire housing actually rotates. This housing is what has the permanent magnets actually attached to it. Inside is the stationary coils, the stator, let's call it. And as we rotate this via the drive, we're going to rotate the magnets past the coils, and we'll be able to induce some voltage into the coils. We'll be able to pick each stator output off and look at it on the scope. So let's get a look at this thing disassembled. As you can see, I took the tiny little circlip off the back of the shaft for the rotor here that secures the whole rig together. Right? So you can see there's a couple of bearings where the windings, stator. And this is the stator in our case. Now, keep in mind, guys, this is kind of opposite. In reality, the stators, the rotor rotates inside in a traditional automotive alternator. The rotor rotates inside the stator as opposed to this setup where we have the rotor rotating outside. But it makes no difference as far as the induction is concerned for demonstration purposes, right? So here you can see we have 12 windings in the pole pieces, intensifying the magnetic flux that goes through the windings. And here you can see on the, again, it's an out rotor, so this is the part that actually rotates. You can see the permanent magnets which are mounted inside there, and there's actually 14 magnets. Permanent magnets in here are astoundingly powerful, actually, for the size of them. Neodymium, perhaps, don't know. But yeah, so bearing on each end, of course, the end frame there. Then the rotor, of course, slips inside the bearing. And these permanent magnets will suck this up pretty quick. Be careful you don't pinch your fingers. And of course, the whole, again, it's an out rotor arrangement. Very clever indeed. Again, the little circlip goes on the back here to secure the whole rig together. Although there's 12 windings, they're wound in such a manner that it's a 3-phase output. So the only way I can alter the output as far as frequency or amplitude is concerned is by changing the speed of the drive. So let's keep an eye on the scope here. Let me turn this on. I only have the single phase, the yellow phase, displayed on the scope at the moment. So let me just put a wee insert in here after the fact, guys. Take a look at the time base on the screen here. It is 10 milliseconds. Now, Snap-on, the time base is not per division, it is for the entire screen, okay? So the entire screen you're looking at here, the time base is a duration of 10 milliseconds. Why am I telling you this? Because when we look at the waveform in rectified form a wee bit later in the video, the time base actually changes to 1 millisecond on the entire screen. So the rectified wave actually looks much smoother than it actually is in reality. But it's important to appreciate that there was a time base change. I buggered that up in the video. I didn't notice I had changed the time base, but
it is a change in the time base later on in the video. Be aware of that.
So you don't have to listen to this, I'm just going to turn that off. I'll hold the image here on screen, and let's look to see what we have. Now, I don't know if you noticed, when the drive actually spun up, the amplitude increased and the frequency increased. Again, the only control we have over this is this drive speed. Let's get a live trace again. Let's turn it on. There you can see the frequency and the amplitude. Let me slow it down. The amplitude, the voltage output is going to decrease with slow rotational speed, slower, and it will increase. The amplitude and frequency will increase with the drive speed, right? So let's just get something reasonable. That looks about reasonable, right? So again, let's hold this. And I'll turn this off. This is a single phase of the 3 phases that I have displayed here, guys. There is 3 phases that are actually output, but I only have the scope displayed for the sake of simplicity initially here to show you just a single stator, single winding output, right? And you can see here it's a sine wave, 360 degrees of rotation, and then it repeats, right? In a sine wave manner. Let's start it up again. Start the trace. Let's add another phase. Let's hold that image. So now what we have here, guys, is not 1, but 2 phases from the little generator actually output and displayed on screen. So what these are again, it's an imperfect motor here, guys, right? An imperfect generator, so the amplitude of the output is not quite the same. In fact, I've bastardized the scaling. It's not even close to the same, but for the sake of appearances, I've made it look similar, right? You can see it's the same frequency. Of course, it's the same frequency. There's only a single drive with respect to the magnets that are rotating, so the frequency is the same. Doesn't matter what frequency it is at the moment. The amplitude is roughly the same. And you can see, if you could measure it, and I can, but I'm not going to get into that because it would involve a timing measurement and then converting it to degrees, and it doesn't matter. Take my word for it at this point. These are 120 degrees of separation electrically, right? So they're out of phase by 120 degrees. Let's start again. Let's add the 3rd phase. So there's the 3 phases there, guys. Again, let me stop this. Turn this off so you can hear me, and you can see quite distinctly there is quite a variation between the output of the phases. You can see the amplitude on the red phase is not quite the same as the other two, nor is it even actually separated electrically by 120 degrees. But appreciate it, these things are only a couple of dollars, right? You can't expect perfection. It doesn't matter as far as the application is concerned. So for us, let's make the assumption all these phases are 120 degrees apart. 3 phases, 360 degrees, yeah? So this is what the output, these 3 phases, this is the output of the stator on your alternator. Now, of course, your alternator in your car, guys, is not a permanent magnet, right? There's more, obviously the engine speed will vary wildly, you know, let's say somewhere from the low end of idle at 700 RPM-ish to maybe up to, if you're pushing it, maybe 55, 6 grand RPM. So that is a huge variation in speed. Can you imagine the variation in output if there was no way to regulate it? Again, we have no regulator here. Our only form of regulation is the speed, right? So we're keeping it simple. We're simply regulating via the speed, which will alter the amplitude and frequency of the 3 phases output. Make sense? Right. So let me start that again, just so you can appreciate the amplitude and frequency will vary depending on the speed of rotation. Okay. So let me hold that image. Okay. So there's one obvious concern here, guys, right? The 3-phase output from the stator windings, in the case of your alternator, is AC. Your car operates on DC, yeah? Typically, 12.6 volt battery static voltage, and then what, 14.4 operating voltage-ish, regulated between those limits for the sake of meeting load demand and battery charging purposes. Again, that may not mean anything to some of you guys, but we'll get there one step at a time, right? So here's the 3-phase output. Let's see what we can do with respect to rectification. Now, the rectification, as some of you will be aware, is simply a process of using diodes in order to, they're one-way check valves, essentially, guys, right? So the one-way check valve network will actually convert this AC into pulsing DC. So let's get a look at that. So a quick look at the textbook here, guys, will show us an AC waveform. This is half wave rectification, where it's took just the top half, and here's full wave rectification, where it's able to essentially invert the bottom half and toggle it up to the top half through some clever arrangements of a diode. This is basically what we have on our motor here, right? So we have our 3 windings. This is given as our 3-phase output. And this is basically what I have here, guys, in a very rough, very crude construction here, as you can see. And I have my 6 diode bridge network here. So this is effectively what we have. So again, without getting overly complicated here, the AC output from each of the coils through the clever arrangement of this bridge network here, again, essentially electrical check valves, will convert this AC into pulsing DC. So let's see if we can actually hook this up and see if we can make sense of the output. 6 diodes, and all 3 phases are being rectified, and I want to see if we can get an output across it and see what the output actually looks like. Now keep in mind, this is basically a floating ground setup here, guys. I'm not sure if I can go to the case ground on the motor, which I was using as the neutral. That appeared to work, but I'm not sure about that yet. So it's a floating ground. So you'll see here on the scope that I'm not at the 0 line. Again, it's a floating ground, so just keep that in mind. So let's start motoring the generator, in this case. Terminology gets a bit confusing, but I think you know what I'm talking about. So at this speed, nothing. Doesn't appear to be really any output, right? But we know that we can, obviously, as we increase the speed of rotation, we'll up the induction, how much voltage we induce into the windings if we spin the permanent magnets quicker, right? So let's spin them quicker. Let's just watch. So I think you can start to see there, guys. We have a little bit of output. You can see the ripple, and you can see the DC voltage there. So we got faster still. You can actually see the LED is starting to go. Let me slow it down again. So that's a slow rotation. Just pick up the speed gradually. You can see we can actually generate a wee bit of DC here across the bridge, right? A little bit faster. Okay, let me just freeze this so I don't need to talk over this screaming show here. So there's quite clearly our 3 phases. The diode pattern, and if you know how to interpret that, it can actually speak to the state of health of your alternator. Anyway, I don't want to get too involved here, guys. I just wanted to keep it basic for the meantime while we develop the basic understanding of how things work, and yeah, we'll leave it at that. Cheers.